If you have ever wondered about a plunger in a turkey syringe, how exactly does that work? Realize as the temperature inside the turkey rises, the air expands and hence the thermometer pops out. Or if you've ever wondered, if you have an inflated football and if you take it right outside during winter time, it kind of shrinks down a little bit. Or air-filled balloons. If if you bring them outside or in air conditioning, they shrink a little bit, and if you bring it back to room temperature or take it out in the sunlight, it expands back. Or if you have an underinflated tire or a balloon that will be nice and turgid in sunlight when it's warm, what's going on? Hopefully you can recognize all of these are relationships between volume and temperature. So over here, I'm showing you a situation that we have a gas sample which has been maintained at a pressure of 1 atmosphere. Volume is zero point 0.5 liters. Temperature is 200 Kelvin, and as I heat it, if I want to maintain that same pressure, you can perhaps envision that the gas molecules will push against the movable piston and the volume will increase. In other words, the gas is going to go through an expansion process during this heating process, provided the pressure is constant and the number of moles that are present are constant as well. What that means is that volume is directly proportional to temperature, and in other words, V over T should be some constant. So one can say if you had two situations where you had an initial volume which is being maintained at an initial temperature, and you're going from that through an expansive process or compressive process to get a new volume, then the temperature will change as well. So V1 over T1 is equal to V2 over T2. What's important is that the temperature will have to be in kelvins. Whatever are the units of volume V1, same will be the units for V2. Now, let's see if we can actually put things in perspective and work on this problem. The question here is, a sample of CO2 at 35 degrees Celsius has a volume of 8.56 times 10 to the negative 4 liters. What would the resultant volume be if we increase the temperature to 85 degrees Celsius when moles and pressure are constant? So we know from Charles' law that V1 over T1 is equal to V2 over T2. Let's see what kind of information we have. We have been maintaining a sample of CO2, so we have an initial volume, the initial volume V1, which is 8.56 times 10 to the power of negative 4 liters. The temperature has been given to be 35 degrees Celsius. Realize I just said a couple minutes ago that the temperature has to be in Kelvin, so you will need to add 273 to this. That will give you 308 Kelvin. Volume is what we are seeking, the final volume. And the final temperature is 85 degrees Celsius. Again, you will need to add 273 to that such that we have a 358 as the final temperature. So hopefully setting this up, hopefully you can see that V2 is going to be equal to 8.56 times 10 to the negative 4 times 358 divided by 308, and we are going to solve for V2. So on my calculator, I'm going to punch in 8.56 times 358, 308 and it comes out to be 9.949 times 10 to the power of -4. If you wanted to go with the significant figures, you'll report it as 9.95. 9.95 times 10 to the -4 liters. Realize something here. We are increasing the temperature from 35 to 85. So you expect the volume to increase. You expect this to be an expansive process. So the result that we got, that does make sense. So now if I combine the Boyle's law and the Charles law, so Boyle's law was pressure being inversely proportional to the volume, and Charles law is volume being directly proportional to temperature. Combining both of those, we can say that P1 times V1 over T1 is equal to P2 times V2 over T2 again. Temperatures are what need to be in Kelvin. Any units for pressure or volume will work. Let's see if we can put things in perspective. We are given that oxygen is normally sold in a 49-liter steel container. So this is a cylinder, let's say. This is the steel cylinder. The volume for this is 49.0 liters. The pressure that is maintained is 150 atm. What volume would the gas occupy if the pressure was reduced? So we have a little nozzle and we are just going to release that, and it's going to come from 150 to 1.02 atmosphere. That means the atmospheric pressure. So all we have done is we have just opened the valve. And the temperature has been raised from 20 degrees to 35. Volume is what we are seeking. So understand that we know P1 times V1 over T1 is equal to P2 times V2 over T2. And now when we plug in the numbers, we can easily say that 150.0 times a 49.0 divided by 293. How did I get 293? Because 20 plus 273 is 293 Kelvin. And likewise, I get the right-hand side of the equation to 1.02 atmosphere times V2 divided by T2. Now that is 35, so 35 plus 273 is going to be 308 Kelvin. So we are going to solve for V2. I am going to punch in on my calculator 150 times 49 times 308 divided by 293 comes out to be 7726. 7726.3 liters. And that makes sense because if you had confined under high pressure, low volume, now that you have completely released it by nearly a factor of 150, then the volume is bound to change by approximately that factor, and realize it's going to increase a little bit more because the process also requires a little bit of expansion, going from 20 degrees Celsius to 35 degrees Celsius. Okay, let's then talk about the Avogadro's law. Avogadro's law essentially relates to the amount of a gas to its volume. So what it says is equal volume of any